Hey everybody, it's Miss Bettis. So today we're going to be talking about quadratic functions and the different transformations, but more specifically we're going to be talking about the vertex form right there of the quadratic equation. And most mathematicians like the vertex form because just like yesterday, that a value, if it's positive, it's going to be opening up. And if it's negative, it's going to be opening down, happy face and sad face, like we talked about yesterday. But that H and this K are going to give us our vertex, hence the name vertex form. So we're going to start off by just kind of talking about the first 6 problems right here, and I'm going to do a rough sketch of each of these. I want you to plug in these equations, though, into your calculator after this video so you can fill in your tables. So let's actually take a look at the graph for problem number 1. So this is the most important one. This is our f of x. And whenever we talk about f of x for these next couple of problems, this is what we're referring back to. So this is the parent function, x squared. So as I plug in these x values into the x value in my equation right here, I'm always going to square it, meaning there's 2 of them. So when I plug in -3, it's like saying -3 times -3, which would give me 2 negatives, gives me a positive. 3 times 3 is 9. And we repeat the process for the rest of the table. And it's important to note, as we're looking at this table, if I was to give you a table, you'd be able to tell if it's quadratic or not and where your vertex is based off the fact that you're going to have numbers that repeat when we deal with quadratics, the 9s, the 4s, the 1s, but you'll always have one ordered pair, that does not repeat. In this case, it's 0, 0, and that is our vertex. And remember from yesterday, your vertex is either your highest or your lowest point, depending on if it's happy or if it's sad. We know our a value is a positive 1 because there's no number there, so that means it's happy. We know it's going to be opening up. So I'm going to go ahead and plot these points real quick. Alright, there we are. And let's go ahead and connect that. Again, like we said earlier, like we predicted, it was positive. Ooh, hopefully yours looks way better than mine. It's positive, so it's opening up. We could tell, looking at our table, that it was quadratic. We knew our vertex was 0, 0. So this is the parent function, and we're going to be comparing all of our graphs to this, and our table will be compared to that right there, our y values. So as I go and look at problem 2, I notice that I still have that x squared from the parent function, but now I have a 3 out front. So it's like saying 3 times my f of x, the parent function. So I'm multiplying 3 times it. And when I do that, what I'm going to end up getting is a graph, a function that, it's a function because it passes the vertical line test, that looks like that right there. So if I was to compare the two, automatically I can see that this new graph that I have, let me make it a little darker for you, it looks skinnier compared to the parent function. So what we're really doing is we're taking this original parent function here and I'm pulling it in like a vertical stretch. So think of like Play-Doh, if you will. Comparing the two, I'm leaving my vertex at the origin. I'm just pulling these arms, these arrows, up, which makes it appear skinnier. So what we do is we call this a stretch. So if a 3 in front makes it stretch, what are we going to say a 1/2 does? So before we answer that question, let's go ahead and write it like we did for problem 2. It's 1/2, and then you still have that parent function, so times x squared out there. So if a 3 made it stretch, what would be the opposite of stretch? We would say a compression. And again, just like the other two graphs, I'm still going to start off at the origin. My next point is going to be in the 0.5s. So my graph is going to look something like that. Again, if I compare it to the parent function, this one looks a lot wider. But again, just we're doing opposite of what we did to the stretchy smiley face yellow guy. We're squishing him together, we're making him compact, so he's going to appear fatter. I've heard some people say fat fractions, so if you have a fraction out front, it's going to make it appear fatter. But for your EOC and your STAR test, you're going to see the words stretch and compression. So being able to identify what those words mean and what it looks like on a graph is super helpful. All right, let's knock out these next 3. So for number 4, we have a negative out front, and that would be like, say, -1 times our f of x, because we still have f of x there. And what that's going to end up doing is it's going to reflect, and more specifically reflect over the x-axis, which is why our graph is kind of shaped a little bit different here. Just like the others, it's going to go through the origin, like the parent function, and it's going to be almost identical to the table from number 1, except we're going to have negatives now. So that looks like this. And there you go, just like we said, it reflected over the x-axis. And just remember, reflection is like a mirror image. All right, number 5. So number 5, instead of putting something in front of, we're now putting numbers behind the f of x. So for this one, we're going to have our f of x, our parent function, as represented by the x squared, plus 3. And what happens when you add or subtract, it's going to move the graph up and down. So if it's a plus, this is going to be a shift up. In this case, it'd be a shift up of 3 units. And we're saying units because in the real world, we can deal with feet or meters. So let's go ahead and graph this one. So there's a very rough draft, and unlike all these other functions, we're not anywhere near that origin. Remember, we just took that graph and we pushed it all the way up. So if we added 3 at the end and it moved it up, what do you think subtracting 4 would do to our f of x? Hopefully you're thinking it's going to be a shift down of 4 units. Our x squared, our a value is a positive 1 again, so it's going to be opening up. So instead of starting at the origin, I'm going to count down 4. It's 1, 2, 3, 4. And then I would graph it the same way as I did before. Or I could take those numbers and subtract 4 from all of them and get my new graph, which would look like this right here. All right, let's go on to the next page. Or think about these little stretchy toys, these stretchy guy toys. The feet would be our vertex. So we're going to pretend like his feet are at the origin still. And his head was one of the points. But as I stretch him up, he's going to look longer. It's going to also look skinnier than where he was originally. So if I go back to my graph, so for problem number 7, it's just being able to look and identify if it is a stretch, a compression, a reflection. Did it move up? Did it move down? So we're going to run through these real quick to make sure we're all good with those. All right, so problem number 7, part A. We notice that we have a 7 out front. So 7 makes it out front, makes it like problem number 2, which was a stretch. Ooh, not the best color to pick. And then the +3 at that end made it go up 3 units. This negative out front was a reflection over the x-axis, and that -6, it moved the graph down 6 units. So that's B. Let's look at the last two before we flip the page. So for C, you have the 1/2. Remember that fraction, fat fractions, means it's going to actually be a compression. So compressed. I'm just going to put compress. And then the +2 means it went up, oh, not 2, sorry, 22. Up 22 units. Now this last one, we have a reflection. We have a 2/3, which, again, fat fractions, so fat means it's compressed. So comma, and put comp for compression. And then that -15 at the end, it shifted down 15 units. All right, we're done with the front. Let's go to the back and finish this up. All right, so problem number 8 is the actual parent function again. So they are nice enough so that way we don't have to flip back and forth. So I already did that for you. I'm just going to relabel it f of x. Now, for these last two, we're actually changing the value of x. We are adding and subtracting inside the parentheses. So what that would look like in our function notation, let's zoom into number 9. If I'm writing it in my function notation, it would be f and then x minus 3 with it. And what this is going to do, the way it's easy for people to remember is think about your x. Your x lies. So when I think of a -3 value, I think negative goes to the left on my number line. But remember, our x lied, so that's not correct. Instead of going to the left, I'm actually going to go to the right. So if you see a negative number, it's going to go to the right. So what this graph looks like, instead of going at the origin, I'm going to go 1, 2, 3 over, and then I would have my graph. And then just like that, with number 10, I would write that with my function notation would be f of x plus 2. Again, when I think positive, I tend to think, oh, positive is that side of the number line on the right, but it's paired with that x, so that's wrong. I'm really going to the left. So anytime you see this, it's going to be going to the left, and then however many times that number is. So instead of starting at the origin, I'm actually going to go 2 over, and I would have my parent function just shifted over. Again, I'll let y'all fill in the tables with your calculator. Let's go to number 10 and 12. I'm sorry, it was 11 and 12. So for 11, I know it says to sketch it, but what we really want you to be able to do is find the vertex from the vertex form. So the vertex form is on the front of your page. It's y equals a parentheses x minus h quantity squared plus k. And your vertex is always h comma k. So if you know the numbers that are here and here, you're good to go. So in this case, we're going to be looking at that +5 and that -3. But notice our equation has a negative right there. So in order to make this equation a positive 5, I need to have two negative signs, because we know two negatives give us a positive. So my actual vertex is -5, comma, -3. The common mistake is they'll take that 5 and that h value and keep the sign. Remember, your x lies to you, so you always have to think opposite. So if it's a +5, when I write my vertex, it's a -5. And if you know your vertex, you know your axis of symmetry, AOS. It's going to be x equals, and then whatever that x value is, in this case, -5. All right, to summarize everything, problem number 12. So go ahead and take a second and pause the video before it ends. That way you can copy down the summary of everything that we've discussed today, and that extra part way at the bottom, you discovered vertex form of a quadratic function. What is the vertex of the parabola given the actual vertex form? We just talked about that. That is going to be your h comma k, but be careful about that h sign, because you got to change the sign. Your k stays the same, the h is what changes. Alright, so you have a paper attached to that. When you're done, go ahead and get started. Have a good day, guys.